Hello students, in this video we'll prove Kepler's third law. From previous videos, we've shown Kepler's first law, Kepler's first law said that in polar coordinates, the trajectory of a planet in orbit of one body around another is given by BE over 1 plus E cosine theta. That was Kepler's first law. And we also saw from Kepler's second law that r squared d theta dt was a constant. So those were the two laws that we had from previous videos. Now what we're going to do is we're going to notice that if I put this first law into Cartesian coordinates, what we'll see is the following. If we multiply this equation by 1 plus BE cosine theta, this becomes r plus E, and then r cosine theta is x. And we have an E times x is equal to BE. So this equation becomes the square root of x squared plus y squared plus EX is equal to BE. And if we expand this out, what you'll see is the following. Expanding this out, and this is just a good algebra exercise, expanding out, we're going to get something like this. We're going to get x plus a constant h squared over a squared plus y squared over b squared is equal to 1. In other words, I can take this and turn it into an ellipse. That's a Calc 2 example. And it turns out, what is this a? This a is going to be be over 1 minus e squared. And the b, by checking this, will be be over the square root of 1 minus e squared. And now since e is between 0 and 1, since we have an ellipse, right? E is between 0 and 1, the eccentricity is between 0 and 1. We know that this expression, the denominator of b, is going to be larger than the denominator of a, so b is smaller than a, so 2a is the length of the major axis. So 2a is the length of the major axis. Okay, excellent. All right, good. And so now what can we do? So now I'd like to recall the area of an ellipse is pi AB. That follows from Green's theorem. I can link that. We prove that in another video. And so this implies that A, the area of this ellipse, is going to be pi times b squared e squared over 1 minus e squared to the power 3/2. That's the area. Now I can also use Kepler's second law, right? So let's let t be the period of the orbit. Then if I integrate from 0 to t of r squared d theta dt, then that's going to give me what? That's going to give me just the area inside the, well, c, of course, there's a constant c over there from the constant, c times the area. Okay? Excellent. Now this, of course, is just going to be what? This is going to be the area, but then, of course, this is going to be c times the period. C times the period, because it's the differential from 0 to this, and that's going to be the area. Okay? So it's c times the period is equal to the area. So now what can we do? So now let's look at the length of the major axis. The length of the major axis is this over here. And so now what I want to do is if I took this, if I look at the a and I squared it, what would I conclude? If I looked at a squared, I would get what? A squared is really c squared p squared, c squared t squared. I'm calling t the period, so c squared t squared. That's what period is. And the area squared is really pi squared b to the 4th e to the 4th over, if I square this, I'm going to get 1 minus e squared cubed. Okay? So that's what the area, formula for the area squared, or a constant times the period squared. Now if I look at 2a and I cube it, now 2a cubed is 8a cubed, right? And that's going to be b cubed e cubed over 1 minus e squared cubed. Okay? And now from this, we see that a cubed So a cubed is b cubed e cubed over 1 minus e squared cubed. We see that these expressions over here, c squared t squared, looks like what? 1 over e squared cubed, and then some constants over here. So what we've just shown over here is that these two expressions are proportional to each other, so hence t squared and 2a cubed are proportional. And of course, you can work out what the exact constant proportionality is, right? So those two expressions are proportional to each other. And now we can conclude that the square of the period and the length of the major axis cubed are proportional, and that's the Kepler's third law. So this is Kepler's third law. Now, of course, Kepler's third law relies heavily on what? Relies heavily on the first law and the second law, which required a lot of work using differential equations. So this all ties in together with the theory of differential equations and Newton's law of gravitation. Thank you very much.